Okay, welcome back. We're going to do one more example from section 4.7. This time you're just looking at the statement of the problem. So let's get right to it. So a person wishes to make it from point A to point B, which are located on opposite sides of a river, and they want to do this as quickly as possible. Okay, so the person wants to start off at point A over here and make it down to point B down here, and the objective is to minimize the amount of time. And how she's going to do it is she's going to select some point D on the opposite shore, somewhere between C and B, and row a boat from A directly to that point D. All right, and then continue running along the shore from wherever D is down to B. All right, so that's how the journey is going to go. This person can row her boat at 6 kilometers per hour. Okay, and she can run just a little bit faster at 8 kilometers an hour. And the question is how to choose that point D to minimize her time, right? Like, for example, like the old saying is the shortest distance between 2 points is a straight line. So maybe she just wants to row from A to B. That's the smallest distance. But I don't know if that's the smallest time because she can't row quite as fast as she can run. Yeah. I mean, maybe given that she can run faster than she can row, maybe the idea is, look, row as little as possible, row straight over to C, and then run the rest. Maybe that's optimal. Or maybe it's somewhere in between, and that's the question, where? Where should she aim for if she wants to minimize her time? Okay, so that's the problem statement. You should stop the video and kind of think about it if you need to. But let's just continue on here. So I've got the same diagram. I want to minimize time. You, like me, probably know the distance is equal to rate times time. If you multiply the rate by the time, then you get the distance traveled. So it follows from that that time is distance over rate. So that's how we're going to break her journey down. I'm thinking of her total time as her rowing time plus her running time. Yeah. So I know the rates for both rowing and running. So I just need to know the distances, and then I can write down how much time it'll take. Okay, so over here, I've already drawn in the picture kind of a coordinate system. You can see that I'm calling on the x-axis, or sorry, on the bank with C and A, I'm going to call the x variable 0 at C. So it would be 8 down there at B. They're 8 kilometers apart, measuring x in kilometers. And I'm going to give a variable name to this point. So I'm basically transferring the problem. I'd like to choose x to minimize this time. Okay, so one of the distances is this rowing distance, which is the hypotenuse of a right triangle. And that right triangle's leg lengths are 3 and x. Yeah. So the hypotenuse of a right triangle with legs 3 and x is the square root of x squared plus 9. So that's her rowing distance. So down here in this formula, I'm taking that rowing distance and dividing it by her rowing rate. That's her rowing time. Likewise, if x is located x units from C and B is 8 units from C, then the remainder, the distance from x to B, must be 8 minus x. It's the difference. So I take that 8 minus x, that's the distance that she has to run, and I divide it by her rate that she runs, 8 kilometers an hour, and that would give me the time that it will take her to run that distance. So if I call t of x the total time required as a function of x, then it's the rowing time plus the running time. That'll be measured in hours. And we have a closed interval problem here. X is somewhere between 0 and 8. So we won't make a table, we won't make a first derivative test sign chart. We're going to make a table of values. We have our two endpoints, 0 and 8. We can plug them into t now if we wanted to. But the question we have to answer is, are there any critical points? Are there any values that make t's derivative 0 or undefined for between 0 and 8? Because if there are, we need to include them in our table as well. Fermat's theorem says they're potential extrema. Okay, so stop the video, differentiate t of x, and simplify it as much as possible, then start it back up and see if you agree with me. I've already got it written out, so we're going to just proceed here. I wanted to get rid of those lines, and I forgot. So here we go. So I'm taking my derivative here. I'm going to use the chain rule, the sum rule, every differentiation rule I know. I'll just kind of walk you through the computation. So I've got a constant factor of a sixth. I put that out front. Here I'm differentiating my square root function. It's 1/2 the thing to the minus 1/2. This 2x is by the chain rule. It's the derivative of x squared plus 9. Okay, second term has a constant factor of 1/8. Derivative of 8 minus x is -1. All right, so now I'm just going to do some algebra. We can just reveal all of this and look at it all at once. So all I did over here is I canceled my 1/2 and my 2. I've got an x upstairs. I wrote the -1/2 power as a square root in the denominator with the sixth, subtracting my eighth. Moving over here, just get a common denominator. So I just really kind of cross multiplied 8x minus 6 times that thing over the product of those things. And then looking at this expression, that's my simplified derivative. The denominator is never 0. The square root of x squared plus 9 is at least 3, so the denominator is never 0. I have no bad critical points. So the only way to get a critical point is for the derivative to be 0, and that can happen if and only if the numerator is 0. Okay, here I included a lot of detail, but solving an equation with a square root, basically the idea is you isolate the square root and then square both sides of the equation. You can pause this and go slower if you want, but that's all I did. Combined like terms, divide by 7 and take square roots. I get x is plus or minus 9 over the square root of 7. Minus 9 over the square root of 7 is not in the interval of consideration, so I don't count it. So now I can proceed. I've got my endpoints in my table. The one and only relevant critical value is 9 over the square root of 7. And what am I going to evaluate those things in? I'm going to evaluate them in t of x. Yeah, so I take each one of those values and I plug it in here one at a time and compute out the value. All right, so for example, if you take x to be 0, we could just talk through one of these things. Well, the numerator of this just becomes 3. So I get 3/6. Yeah, 3/6 plus 1, right? 3/6, that's 1/2 plus 1, that's 1.5. That's the time in hours. If she were to, when x is 0, remember that would be row straight across and run all 8 kilometers. All right. How about if she rode the whole way? If x is 8, there's no running at all. That takes slightly less time. So it turns out that she can run faster than she can row, but it doesn't make up for that straight line distance. So if it was just a matter of those two, she'd be better off rowing the whole time. But if you plug in our critical value and you evaluate it out, you get that number exactly, or 1.33, and that's our minimum. That's the smallest time value I see. That's our minimum value, 1.33 hours. Yeah, so that's the solution. So the answer to the question is she should row to a point D that's located 9 over the square root of 7, or approximately 3.4 kilometers downriver from C, and run the rest. And the total journey is going to take her about 1.33 hours, or 1 hour and 20 minutes. All right, so I hope that was useful. You can soak that in, and when you're done, if you want to take a break, I would highly recommend that you switch over to your favorite web browser and Google the phrase Elvis the Calculus Dog and enjoy that 5-minute video. All right, I hope these examples were helpful, and maybe I'll see you in an office hour. Thanks for listening.